This time I'd like to use a double integral to compute an area between two functions. Now when we're using a double integral to find area, then there's no particular function that we'll have to use in our integrand. We can just use a 1. So the first thing to decide is how we want to cut the shape up. In the past we had the option of cutting the shape up along the x-axis or the y-axis. It was our choice. And the same is going to be true here. However, because we're doing a double integral here, we're going to actually cut it up both along the x-axis and the y-axis. But we still have to determine the points of intersection. So let's start off with that. To find the points of intersection, set one formula equal to the other. Here we have x alone for both, so that means that I can take this and set it equal to this. Alright, we get y squared minus y minus 2 is 0. I'll try to factor it. Alright, so we get y equals 2 or y equals negative 1. I'll plug in the y values that I got into one of the formulas here. The next thing to decide is the orientation of what I would call the mains. The mains are the slices that are either horizontally or vertically oriented, and this is the first integration that gets done. Now, if I did vertical slices, I see that I would have to change the function that I'm using halfway through the integration. I'd rather not do that. It would have to be a piecewise defined thing. I'd rather just keep it consistent. So I'm actually going to prefer my mains to be horizontal strips for this shape. So that is the first integration that gets done. And it's going to be a dy type of differential because that is the height of each main. So we're going to start with a double integral, and we're not going to put any function inside the formula this time because we don't actually want the height of it. We don't want the z dimension. So we could just put a 1 there. That's it. But now we don't want to use dA. We'd rather turn it into either dx dy or dy dx. And since I'm cutting the strips up horizontally here, I'm going to make my limits from y equals negative 1 to y equals 2. And then on the other side, I just want to put a dy, and these are going to be like parentheses. Okay? That's the outer integration. Now we need to do the inner integration. And what that's all about is cutting each main up into little pieces of area. Now you cut the main up first, and then you go through the whole strip, integrating along the x-axis. So to achieve that in a double integral, what we want is we want an inner integral from x equals something to something else, and then we're going to put a dx here so that the dx matches with the inner integration sign. But now comes the tricky part. What will be the limits? The strips don't all have the same starting and ending points. they're based on where you're located in the y-axis when it comes to how long they are, where they start, and where they end. So we actually need to put formulas here instead of just single numbers. We have to go from this function, which I'll call g of y, to this function, which is f of y. All right, luckily we have the formulas already solved for us right here. So our g of y is going to be y squared. That's the lower function. And f of y will be y plus 2, and that's the upper function. Now why do I say it's the upper function? Because it's more positive. It's more in the positive x direction than this curve. And we want to go from g of y to f of y. And this will just be a 1. Okay, so let's fill in the formulas. We'll have x equals y squared and x equals y plus 1. We now want to take the antiderivative of the 1 and leaving everything else the same. Bring our limits over and our dy. Now we want to plug in the y plus 1 just like we would any number, f of b minus f of a, right? So it will become y plus 1 minus y squared dy. Now let's get an antiderivative for all this. And use our limits from -1 to 2. I get 3 halves, or 1.5. Let's check our work with Symbolab. We'll go from -1 to 2 in the y, and from y squared to y plus 1 in the x. There we go.